Let's go over these questions. Diffusion-weighted imaging typically involves at least two acquisitions. So one acquisition is going to be the diffusion-weighted image. That's also known as B1000 or B800 or B500, etc. It has some positive number after the B. And all that means is that there's a bipolar gradient magnetic field somewhere in that pulse sequence. And the stronger the gradient and the longer that gradient is on is going to determine how large that number is. Okay, so that's the diffusion-weighted image. We're also going to have the B0, and the patient has to sit still while each of those sets of images are acquired. The ADC, remember, is not acquired, it's post-processed. It's a fancy subtraction of B0 minus the diffusion-weighted image, B1000, for example. What does dark signal on the ADC represent? So we all know it represents restricted diffusion, but I want you to understand why. So we know that because there's relatively little signal loss from B0 to B1000. So remember, the B1000, what are we doing? We're applying this bipolar gradient magnetic field. The first lobe is going to dephase the spins. So as long as there's restricted diffusion and things stay in their columns, when we apply a gradient magnetic field with the opposite polarity, it's going to rephase the spins, and so we're going to restore phase coherence. When you restore phase coherence, you have phase coherence, you're going to preserve signal. So that's the reason that the signal doesn't really change a ton when you go from B0 to B1000 if there's restricted diffusion, okay? And that's going to be represented as dark signal on the ADC. A couple other points. So when we see this white signal in the left centrum semiovale on this diffusion-weighted image, that's not because those cells have gained signal relative to other parts of the brain. What's happened is that they've lost less signal. So that's an important thing to understand. Overall, we're losing signal. When we go from B0 to DWI, overall we're losing signal. The reason why this looks so white is because it's lost less signal compared to the rest of the brain. Another point, the bright voxels on the ADC image don't represent high signal. What that actually represents is a large loss of signal. So again, a simpler way to think about it is that white signal on an ADC represents free diffusion and dark signal represents restricted diffusion. But anyways, it's counterintuitive, at least it was to me initially, that white signal represented a large loss of signal, because that's not typically what that means on other sequences. Usually white on another sequence means there's a lot of signal. So it's actually the opposite in ADC. It means there's a large loss of signal from B0 to B1000. Okay, why was the ADC dark relative to the brain parenchyma on the initial study? Well, because of restricted diffusion. Why is it mostly isointense on the follow-up study? Well, that's due to a phenomenon known as pseudonormalization of the ADC. So let's talk about that. So pseudonormalization of the ADC means that the ADC looks normal, but in fact, there's two pathologic things that are happening. We have some infarcted cells that have lysed their cell walls, and the water is extracellular and freely diffusing. That's going to have a bright ADC. And then we have some other cells that are dead, but their cell walls are still intact, and so the water remains intracellular, and their diffusion is restricted. So the ADC is going to be black. So when we have a mix of these infarcted cells, some with intact cell walls and some with lysed cell walls, what's going to happen is that the ADC is going to actually average out and look normal, when in fact the situation is actually not normal. So if you see bright DWI signal and normal signal on the ADC, ask yourself, hey, maybe this could be a subacute infarct, especially if you have a prior study where you clearly saw that it was acute.